Hello everyone, I'm David Spencer, Director of Technical Marketing at Colsar, and in this presentation we're going to look at some of the synchronization requirements for upcoming 5G cellular networks and how Colsar can help you solve those requirements. First of all, a legal disclaimer that any material presented in this presentation is proprietary and confidential and should not be distributed to any third party without the consent of Colsar. The features that we mention here are in some cases advanced roadmap features, which it is Colsar's intention to incorporate into products in the future, but we make no guarantees about that at this time. Okay, so what are the needs of synchronization for 5G networks and in fact some of the 4G advanced networks that are paving the way towards 5G? One big change that we're seeing as we move to 5G is splitting of the what was traditionally the base station function into a digital portion, the baseband side, and a more analog portion, the radio side. Traditionally, those functions have been co-located either in the same unit or in closely linked units connected by proprietary interface such as CPRI, which doesn't have any network-wide synchronization requirements. However, as part of the driver towards distributing the network for 5G, we're seeing much more application of centralized baseband functions that then connect over a public or semi-public network to the radio units. This portion of the network is referred to as the front haul, to distinguish it from the back haul, which is the portion that connects the baseband side back into the core of the network. So on the assumption that the network will be split like this, one can define a number of synchronization classes that define the level of synchronization that is needed for each particular portion of the network depending on the application, and they can be seen here in this table. The first of those is synchronization category C, which relates to the backhaul requirement, and this is, as you can see, 1.36 microseconds. This is saying that the baseband processing portion of any base station has to be aligned to within 1.36 microseconds of any other base station. And in fact, this is an absolute time requirement, so not only relative to each base station, but also relative to its real time, or UTC as it's more correctly called. Then the other requirements we see here are relating to the frontal portion of the network. So this is the portion between the baseband processing and the actual radio head. The requirement here depends on the particular application. If carrier aggregation is being used, where multiple carriers are used to increase overall bandwidth, then we have a requirement here of either 110 nanoseconds or 45 nanoseconds, depending on the exact nature of that, in particular whether the carriers are on adjacent frequencies or not. And then if we try to use some of the advanced technologies of 5G, such as distributed MIMO, where we have effectively a virtual antenna distributed across multiple radio units, then even tighter synchronization requirements are required, as you can see from the 10 nanosecond Class A plus requirement here in the table. So how do we practically achieve such synchronization levels in a network? There are two key technologies that will come into play. One is the use of IEEE 1588 PPP boundary clocks to improve the time alignment across the network as a whole and reduce the effects of accumulated noise through the network. To understand how these work, you can see the top diagram here is what we call a non-PTP aware network. So this is a network of a number of switches that just pass the IEEE 1588 packets as if they are normal network traffic. They can't tell the difference between timing packets and video packets and voice packets and whatever else might be on the network. So here we have the master device at the left-hand side, and we have the slave device that is recovering time at the right-hand side. The messages just pass backwards and forwards through the network and get subjected to any interference on the network, such as packet delay variation, which is the noise that is introduced when packets get delayed by other packets on the network. You have to remember that these messages are just part of the overall traffic and they're competing with everything else on the network. The advantage of such networks like this are they are very simple to deploy because they don't require any time awareness within the network itself. Therefore, they're low cost, simple deployment, very easily usable on existing network infrastructure. But unfortunately, the added network noise means that they cannot achieve the tight synchronization levels that will be needed for fronthaul. So that's where the concept of a boundary clock comes in, which you can see in the lower diagram here. So now, instead of just normal switches or routers at each point in the network, we have what are called PTP boundary clocks that actually recover time, regenerate it, and then pass it on to the next node. So if you compare the two diagrams, you can see, whereas in the top diagram we had all the messages went across the whole network in one go, now we have each message goes one hop at a time, each node is recovering time and then passing on to the next node. This allows us to eliminate most of the effects of noise that occurs through competing traffic on the network, and therefore gives us much better performance at the end of the network. Of course, to implement this, we have to put these boundary clocks at every point in the network, which, if we're trying to do this in an existing network, will mean equipment upgrades. If we're doing it in a new network, it will still be additional expense because there will always be some price penalty of a boundary clock over a simple switch. But in reality, such an approach is needed to achieve the synchronization levels we're looking for. However, even boundary clocks on their own are unlikely to provide good enough performance, so we need to use them in conjunction with physical layer timing support in the form of synchronous Ethernet. Now, to understand what synchronous Ethernet is, you first need to look at what Ethernet in general isn't. Ethernet is designed as an asynchronous transport, which means that packets can be sent on the network without any frequency synchronization between the two endpoints. As originally defined, Ethernet allows for the clock at each end to be implemented with a simple crystal that's accurate to plus or minus 100 parts per million, which is obviously no use for a very precise timing at all. However, there is nothing in the Ethernet standard to stop you using a very precise traceable clock instead of a free-running clock, and that's exactly what synchronous Ethernet does. So it actually generates the Ethernet packet clock from a traceable source such as a GNSS receiver, often the same time source that is driving the 1588 Grandmaster. And then that frequency gets transported down the chain of Ethernet devices through the switches and the boundary clocks. Each one of those devices includes a filtering function which removes any noise that has been accumulated on the network, cleans up the clock in much the same way as the boundary clock cleaned up the PTP traffic. And the result is that the end node, so the radio head, for example, in a 5G application, can receive both clean 1588 traffic for time alignment and clean synchronous Ethernet clock for frequency alignment, and the two of those can be used together to achieve much better time alignment than could be achieved with just the 1588 portion alone. There's lots of subtleties in the synchronous Ethernet standards, different ways it can be implemented depending on where the clock comes from. We won't go into details of that in this presentation, but suffice to say that adding synchronous Ethernet to a 1588 network will always provide some degree of performance improvement. If the network is architected from the outset to support both 1588 and synchronous Ethernet, it will typically operate in what's called a coherent congruent mode, where the two can be thought of as living hand in hand. So wherever there's synchronous Ethernet, there's 1588. They take the same path through the network, and that allows us to get the best level of performance out of the network. However, it is possible to put synchronous Ethernet into portions of an existing network without having that congruency and still get some performance improvement. So the standards bodies have been putting a lot of effort in the last couple of years into defining standards for synchronous Ethernet in what they call full-on path or partial-on path support networks. So the first of these is defined in a standard called G8275.1, and deals with the full on-path support case, which is a situation where you build your network from synchronous Ethernet-capable boundary clocks from the start. So every piece of switching or routing equipment in the network is capable of handling both 1588 and synchronous Ethernet. You see from the diagram here the original reference model that was created for this standard defines up to 10 hops in the network, so 10 switching or routing devices. Each one's allowed to introduce a certain amount of error to the timing, both in terms of a static error, so an error that will always be present, and then a dynamic error. So think of it as a variation on top of that static error. And then there's additional allowance for an error in the actual original time source and a holdover budget at the end of the network if some node should fail and we have to go into holdover. There's a budget for that as well. The result being that the target is to provide 1.1 microsecond synchronization across the network as a whole, which allows this type of network to achieve the 1.36 microsecond requirement for the backhaul synchronization. But that doesn't mean we can't use this type of network as well for fronthaul. We just have to redefine some of the parameters, so implement boundary clocks that generate less noise than allowed by the first version of the standard, and also restricts the length of the network. So instead of 10 hops, 5 hops, or maybe even only 2 or 3 hops. By doing that, we can use the same approach to get synchronization levels down to a sub-100 nanosecond requirement for the fronthaul synchronization. The second activity from the ITU is in the G8275.2 standard, and this relates to what is called assisted partial on-path support, and is designed to address the case where you have a legacy network, so an existing installed network that you want to be able to at least use for supporting backhaul, but you can't afford or don't want the hassle of having to replace all the network equipment, so you have to make do what is already there. In this case, the approach is to put strategically positioned boundary clocks with normal switching and routing devices between them, and also add a GNSS receiver capability at the end nodes and the boundary clocks themselves to supplement the time alignment that is achieved through the network. By using these two techniques together, you can typically get adequate performance without redesigning the whole network, certainly for the backhaul requirement. Such networks typically wouldn't include synchronous Ethernet, but there's no reason they couldn't. So even though synchronous Ethernet is optional for partial on-path support, it is certainly useful to have it there as an additional timing flow. So having looked at that, how can Pulsar help you with your synchronization requirements for such networks? We have a number of products that are optimized for IEEE 1588 and synchronous Ethernet operation. The first of these is our M88 managed clock engine module. This is a complete synchronization solution in a very easy to integrate module form factor that includes both the IEEE 1588 portion for time synchronization and a very advanced physical layer PLL device for the synchronous Ethernet wander filtering function. This allows the M88 to be used to implement the synchronization function in a piece of transport equipment such as a boundary clock, or indeed be used in the master at the head of the network itself. For end node applications, these tend to be more cost sensitive, so we're looking here at small cells, remote radio heads, next generation radios for 5G. Although the M88 module would be a good technical fit for such products, from a commercial perspective, the price model may not be ideal. So Pulsar has developed a ported software solution that is based on exactly the same software that runs on the M88 module, but can be ported directly to a small cell remote radio head type SoC device, and in the future will also be portable to FPGA-based solutions. This provides the IEEE 1588 slave function as an application running on top of the existing real-time operating system alongside all the other functions that are being run on the baseband processor or on the digital side of the radio head. This solution is optimized for the network types that we just spoke about, so we can achieve good performance with both frequency and time synchronization over both full on-path support and the assisted partial timing support networks. And because it is a software-only solution, it is a very cost-effective option. Now, to add synchronous Ethernet to such a solution, we have partnered with Murata, who are a well-established component vendor, particularly in the high-stability temperature-compensated oscillator space, to develop a unique product that combines a high-stability TCXO along with the synchronous Ethernet wander filtering function in a single small cost-effective module that can be directly controlled over an SPI interface from the Colsar Q Engine software solution. So the combination of the Q Engine software providing the 1588 portion plus the Polaris smart oscillator providing the synchronous Ethernet portion is what allows for that full on-path support and achieving the sub-100 nanosecond type performance levels. And to illustrate that in the real world, here are some performance results we've captured. This is actually a measurement of a partial on-path support network without any GNSS assistance, but with synchronous Ethernet on the network. So in particular, we're operating over 5 network hops here, so 5 switches with other traffic flowing on them that have no boundary clock function built in, just the synchronous Ethernet capability. And the graphs there are a little hard to read, but in the different test cases that we ran here, the worst case performance was about 90 nanoseconds. So if you recall, the frontal requirement that we were looking at earlier was 110 nanoseconds. So 90 nanoseconds is showing that we can reach that performance over a legacy network of 5 switches, which is a very good step towards achieving the full needs of 5G synchronization. So to summarize, the Colsar solutions are perfect for providing the category C backhaul synchronization, the 1.36 microsecond requirement, and as we just showed, are more than capable of achieving the 110 nanosecond category B requirement as well. As we move towards the even tighter requirements, the 45 nanosecond and eventually the 10 nanosecond requirements, that will require some additional optimizations both at the network level and the equipment level. At the network level, it will require further enhancement of boundary clock capabilities and limiting the network to maybe 2 or 3 hops maximum, or indeed the implementation of a different type of network, such as a time-sensitive network, which uses 1588 transparent clocks, which are almost a competing technology to boundary clocks, and something we won't cover in more detail in this presentation, but we'll include in a future presentation. But rest assured that Colsar is working on solutions that will allow us to achieve those 45 and 10 nanosecond requirements when they become needed in the second phase of 5G deployment. So on that note, I'd like to thank everyone for taking the time to watch this video. Please visit our website at colsar.com if you need more details on any of our products, and reach out to us with any questions you may have. Thank you.